We all know charge comes in two types, positive and negative. Like charges repel. Opposite charges attract. But can this be generalized to three types of charge? Indeed it can. Let's see how this works. With two charges, we can plot their values on a number line. Their values are simply +1 and -1. For three charges, let us plot them as vectors on a 2D plane. Let us call these three charges red, green, and blue. According to the rules of vectors, we see that red plus green plus blue cancels out to 0, which we'll call white. How do we calculate the attraction between these different charges? Recall that the force of attraction between two charges is simply minus the product of the charges. For three charges it is essentially the same except we use the dot product of the vectors. Thus red repels red, blue repels blue, and green repels green. But red and green are attracted to each other with half the force. Green and blue are attracted, and blue and red are attracted. For those who know about quantum chromodynamics, you will know that this is not the same since there are no color-changing forces. In technical terms this is a U(1) squared force, not an SU(3) force. Nonetheless, we can use this model to simulate quark-like behavior. When we start with a load of particles with different color charges, they naturally combine into triplets, in analogy with protons and neutrons. We don't have to use an inverse square law for our simulation, but can experiment with other laws. By negating the three charges, we get three anti-charges: anti-red, or cyan, anti-green, or magenta, and anti-blue, or yellow. In our simulation, three antiquarks form an antinucleon. A quark and antiquark of opposite colors forms a meson. So it is interesting that we can model classically to some extent protons, neutrons, and mesons. However, this simple classical model misses out important things like the discrete energy levels of hadrons. What about more charges? If the charges come in discrete amounts, basically we can turn any lattice configuration into a charge space. The 2D lattices are the square lattice, which is equivalent to two kinds of electric charge, and the triangular lattice, which is equivalent to the color charges. Some other interesting lattices include the 4-dimensional lattice called F4, which has 12 colors and 12 anticolors. The 8-dimensional E8 lattice, which has 120 colors and 120 anticolors. And the 24-dimensional Leech lattice, which has 98,280 colors and the same number of anticolors. A universe with such color charges would contain hadrons with a large number of quarks. The only rule being if any subset of those quarks had charges that sum to white, then these would split off as another particle. Many people have tried to match up the standard model particle charges with charges from lattices, but so far it hasn't quite worked. Despite what some people may claim. In the meantime, let's enjoy some more simulations. You can try the simulations yourself. See the link in the description. If you are good at programming, have a go at generalizing this to more charges. Although you may find you run out of colors. How many types of charge do you think there are in the universe? Leave your comments below. Thanks for listening.